Hey students, today we're going to do Appendix D, which is solving systems of equations using matrices. Matrices come up a lot in linear algebra, which is all about matrices, and in computers. So this techniques that we're going to learn today are really just kind of like an introduction to what matrices are and how they operate. They're kind of fun to work with because they don't have all the symbols and letters that you have when you have your systems of equations. We just get to look straight at the numbers and we keep them organized on a grid so we know which coefficient each number, which variable each number really applies to. And we don't have to worry about all that extra stuff. We just get to look at the numbers. And unlike when we were solving our systems of equations in 3 variables before, where you kept coming up with new equations, now we replace the old equations with our new equations. So we really get to keep our information very contained. So let's take a look at some information on this, and then I'll run through a couple examples for you. All right. So Appendix D, solving systems of equations by matrices. A matrix is a rectangular array of numbers. It can correspond to a system of equations when that system is written in standard form. So for example, x plus 3y equals 5 and 2x minus y equals -4. That's a system of equations. It's written in standard form because you've got x, y, and constant term. We can just pull out the coefficients of that and put it into this rectangular array that we call a matrix. Because we know we're in standard form, we know that the 1 and the 2 are coefficients on our x's, the 3 and the -1 are coefficients on our y's, and the 5 and the -4 over there in column 3 are our constant terms. So that's how this rectangular array just kind of makes it a little simpler to look at once you get used to it. We can do operations with our matrix that are equivalent to elimination operations we were doing with our systems of equations. These are going to be called elementary row operations. Any 2 rows can be interchanged. So I can switch row 1 with row 2. That's really the same thing as just listing one equation before listing the other equation, right? Elements in a row can be multiplied by the same non-zero number. So that's where we would multiply both sides of an equation by some constant term, okay? Elements in a row and multiples of rows can be added to corresponding elements in another row. So this is basically where we add one equation to another. The difference here when we have our matrices is that we're actually going to add the two rows or 2 equations together, and we're going to replace one of those rows with that new information. Okay. Our goal with a matrix is to transform it into a matrix that's in what we call row echelon form. And that's where you have 1s all along the diagonal and 0s below that. The numbers above it are still okay. Once we get to that point, we can translate it back into our linear equations and solve from there using substitution. Or we can do more row operations that get us into what's called reduced row echelon form. And that's where you just have 1s along the entire diagonal, 0s above and below the 1s. And since we have that extra column on the end, those will all be the solution values for your variables, okay? And I'll show you what row echelon and reduced row echelon form look like. So first, let's do a 2x2 example. And when I say 2x2, I mean we have 2 variables and 2 equations. But as you can see, our matrix is always going to have that extra column for our constant terms. Okay. So the way you want to do this is strategic. It's a little bit like a Rubik's Cube, right? If you turn one thing, it can kind of mess up another thing. So we have a strategy to avoid that. What you want to do is you want to start at the top of your first column and whatever you need to do to get that to become a 1. So you probably are going to multiply that row by something to turn that first value into a 1. Then you're going to use addition and replacing the rows below it with additives of that row to get zeros below your first 1. Once we've done that, we're going to move along the diagonal and get a 1 in the next diagonal spot. All right, and then zeros below it, and then keep moving forward. So here's our first step. We already have a 1 in the first row, first column in that corner. So that's good. What we need to do is turn the number below it into a 0. So in order to do that, we just multiply our first row by -2 and add it to our second row. So notice that our first row doesn't change, but our second row becomes -2 times row 1 plus row 2. So we multiply this 1 by a -2, we add it to -2, we get our 0. We multiply this 3 by a -2, we get a -6, we add it to -1, becomes a -7. We multiply this 5 by a -2, it becomes a -10, we add it to -14 or -4, we get a -14. All right, so in order to get zeros in all the positions below our very first 1, we just add multiples of that row to our other rows. But notice we're not actually changing row 1. Okay, we're just changing row 2. And now we've got our 1 and our 0. Then the next step is we go to the next position on the diagonal and we want to turn this -7 into a 1. We want to turn that into a 1. The easiest thing to do is to just multiply our whole row by 1 over -7. So essentially we're going to divide this whole row by -7. The reason turning this into a 1 needs us to multiply or divide is because by multiplying or dividing this whole row, we won't affect the 0. So our 0 will stay put. Okay, so we'll divide this whole row by -7. -7 divided by -7 gives us 1. And -14 divided by -7 gives us 2. So now this is what we call row echelon form, where we have 1s along the diagonal and 0s below them. If this gets converted back into our equation right now, you can see that y is going to equal 2. There you go, y equals 2. And then x plus 3y equals 5. So knowing that y equals 2, we can substitute y equals 2 back into this equation and get that x is -1. So essentially what we're doing is the same thing we did doing an elimination with our systems of equations. We're just writing them in matrix form, which is a little more systematic in how we eliminate variables. And it's self-contained in that we don't come up with a bunch of new equations. We just replace our old equations. Okay. If we didn't want to translate it back after getting it into row echelon form, we could continue on to reduced row echelon form. Okay, so we would go through the same first 2 steps to get to this matrix here, but reduced row echelon form, we would want a 1 or a 0 above our 1s as well. So we can just add, if we want to turn this 3 into a 0, we can do that by multiplying our second row by -3 and adding it to this row, to row 1. The nice thing about that is because there's a 0 in the front, it's not going to affect this 1 at all. So we'll multiply row 2 by a -3 and then add it to row 1. -3 times 1 is -3 plus 3 gives us 0. -3 times 2 is -6 plus 5 gives us -1. Once we're in this reduced row echelon form, our answers or solutions to our variables are actually just the right-hand column. So X is -1, Y is 2. Okay. You're welcome to continue to reduce row echelon form when you solve these, or to stop in row echelon form and go back to your equations and use substitution. Just a reminder, when you want to get a 0 in one of your positions, you should add a multiple of another row to that row. If you want to get a 1 in one of your positions, you need to divide that row by whatever value you have. Okay. Now let's take a look at a 3x3 example. All right, so here we've got 3 equations and 3 variables. We can convert it all into the matrix just by using the coefficients. Okay, since we know we're in standard form x, y, z equals constant term, we don't need that x, y, z and equal sign because we know by the placement in the matrix where that goes in our equation. So step 1, translate to the matrix. And now, first, we're going to fix our first column. Okay. So to fix our first column, since we've already got a 1 in the first position, we don't need to worry about that 1. We want to get zeros in both of the positions below it. So we want to turn this -2 into a 0, and we want to turn that 1 into a 0. In order to turn stuff into a 0, we need to add multiples of another row to that row. So if we want to turn this -2 into a 0, we're going to multiply row 1 by -2, or sorry, by +2, and then add it to row 2. Oh, I guess I'm calling them rows A, B, and C. Hopefully that'll help. So we're going to multiply row A by 2 and add it to row B. But remember, we're not actually changing row A, right? So we're going to say 1 times 2 plus -2 is 0. 2 times 2 is 4 plus -1 is 3. 1 times 2 plus 2 is 4. 2 times 2 plus 5 is 9. All right, so we just replaced row B with row B plus 2 times row A. All right, so the only thing that changes is that one row, and we've changed it in such a way that we now have a 0 below the 1, which was our goal. Now we want to get a 0 below that 0. So we want to turn this 1 into a 0. So in order to turn that 1 into a 0, we're going to have to use this 1 in our first row again to eliminate that guy. So now we're going to add to row C. We're going to add -1 times row A to row C. So -1 times 1 is -1 plus 1 gives us 0. -1 times 2, -2 plus 3 gives us 1. -1 plus -2 gives us -3. And -2 plus -8 gives us -10. So we use addition. That's the reason we fixed this 1 in the first place, is because it's a nice 1 and it's clear what we need to multiply it by to change both of the values below it to zeros. Okay, so we use that 1 to get the zeros below it. All right, and just change one row at a time. Right. So now we've fixed our first column. We've got 1, 0, 0. And we need to go to our second column, and we're going to try to get a 1 on the diagonal there where that 3 is. The nice thing about these row operations is we don't actually have to work that hard to get the 1 on that diagonal. We can just switch these two rows. So we're going to switch rows B and C, and bam, we've got our 1 on the diagonal. It's taken care of. Now we just need to get zeros below that 1. So if we want to turn this 3 into a 0, we're going to use the 1 in the row above it, some multiple of the row above it, to turn that 3 into a 0. So we're going to multiply row B times -3 and add that to row C. We get -3 plus 3 gives us a 0. We get a +9 plus 4 gives us 13. We're going to get a +30 plus 9 gives us 39. That's because we multiplied row B by -3 to cancel out this 3. And then we had to do it to everything else in that final row. Remember, in reality, we're not actually changing row B at all. We're just using a multiple of it in order to change row C. So now we've got a 1 with zeros below it, a 1 on the diagonal, zeros below it. And our last step is we have to turn that 13 into a 1. So if we want to fix our third column, remember when you turn things into ones, with the exception of exchanging rows to make it simple, when you turn something into a 1, we usually want to use division. So we're going to look at row 3. We want to turn that 13 into a 1. So we're just going to divide row 3 by 13. And we get a 1 and a 3 there. Now we're in our row echelon form where we've got the 1s on the diagonal and the zeros below. Here you can see that if this is the coefficient on X, this is the coefficient on Y, and this 1 is the coefficient on Z, we know that Z equals 3, right? If we take this guy and translate it back into equations with their variables, we can quickly see that Z equals 3, substitute that back into this equation to see that Y equals -1, and substitute both the Z and the Y variables back into here to get that X equals 1. Take some time to look at what we did. I went over it really fast. These are very slow problems you need to work through. Remember, be very careful that you're not messing up your negative signs. Check your rows. You're only going to change one row at a time. If you need to write, on the side what you say, what do we change here? This row times 2 looks like, so that you can add it to that other row, that's fine. Make sure you're only changing one row at a time and that everything in that row gets changed. All right. So that's solving systems of equations using matrices. It's a lot of work, but once you get good at it, we actually just program computers to do this for us. But you have to understand the process and how and why it works if you're ever going to be able to program a computer to do it for you. Okay. That's solving our systems of equations. Take your time working through it. Be careful to write carefully and be able to trace back wherever your mistakes are, because usually they're just small multiplication and addition mistakes. All right, so you got to be very focused and take your time so that you don't get frustrated. All right, good luck, and let me know if you have questions.